In this video, I will be discussing the chemical shift in NMR spectroscopy. So NMR instruments use very strong magnets. So if you go over to an NMR instrument, there's usually going to be signs there telling you to not bring your phone or your watch close to the instrument because you don't want to damage the phone or the watch because of how strong that magnetic field in the NMR instrument is. Electrons, however, can shield nuclei from the magnetic field. And the chemical shift is going to come from the degree of shielding that electrons can do on the hydrogen nucleus. Right? So the more shielding there is, it'll be in a certain part of the spectrum. The less shielding, it'll be in another part of the spectrum. And I'll go into that in a little bit. So your shielding constant is very small compared to the magnetic field strength. So to really get the chemical shift, you have to zoom in a lot on the NMR, and the units of the chemical shift are in parts per million, because you have to multiply the shift or the shielding that you get by 10 to the 6th, and that's the units for it. So as with anything, you need a reference for the chemical shift, otherwise the numbers are kind of meaningless. So the reference is usually TMS, which is tetramethylsilane. The reason TMS is used is because you have 4 methyl groups. There is a ton of shielding. So this is set to chemical shift equals 0. So every NMR spectrum you look at will have a tall peak right at 0, and that's the internal standard of tetramethylsilane. So I'm going to draw out just a general, what you'd see at the bottom of an NMR spectrum. And this is indicating the chemical shift here. Let me redraw that again. So the chemical shift. All right, as you move to the right, this is what's called upfield. The atoms near the hydrogen environments are going to be electron donating, right? Putting more electron density because there's more shielding with more electron density. And generally, because you have more electron density, you're going to have anionic character. Right, so think, electron donating groups that are in this way. So there's a lot of, carbons and hydrogens in this area. You won't really see electronegative atoms at all because they're going to be pulling electron density away. And after I do this generalized chart, I'm going to go through and put what functional groups you could expect in different parts of the spectrum. If you move to the left, this would be what's called downfield, and it would be less shielding. Right? Over here, you've got more shielding. So less shielding, that would be, electron withdrawing groups. Lower electron density. And because of that cationic character. So with more downfield, think a carbon with hydrogens next to an oxygen, because that is an electron withdrawing group, or next to a carbonyl. Right? Pretty much the furthest downfield you'll get is a carboxylic acid, because you have two oxygens there that are both going to be strongly electron withdrawing. So just think less shielding, you're going to be near an electronegative atom, because that'll pull electron density away from the hydrogen chemical environment. So here, I'm going to draw going all the way from 0 to 12. So 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I'll put the numbers in just so it's a little clearer when we're looking at it. So the furthest downfield, like I mentioned, is going to be the carboxylic acids. So your carboxylic acids. Then pretty far downfield also will be your aldehydes. A common one you'll see when you're analyzing spectra, right, 8.5 to 7.5-ish range are going to be your aromatics. So think something like, benzene. The area a little less than 7 to around 4.5. This is going to be your alkenes. Right? There's more electron density in an alkene than you have obviously in like a carboxylic acid or an aldehyde, but there's less electron density in an alkene than in just an alkane, because you have that delocalization of the electrons, right? That can form cationic character. Then you're going to get a broad area all the way ranging from around 5.5 down to 1. That could be your OH or NH groups. Sometimes they don't appear on an NMR spectrum, so you don't know if they do, but you'll be able to tell when you're looking at your spectrum if you have that peak. It just might not always be there. Another common area you'll see is between 3.5 and 2.5 or so. You can get your alkynes, so the hydrogen environment with the triple bond there, and then more your ketone. Right, the ketone's so much further upfield than the aldehyde or the carboxylic acid, because you have the carbon here rather than the hydrogen bonded directly to the carbon that has an oxygen on it, and then over here you just have 2 oxygens. All right, so that's why you have the ketone a little bit further upfield. And then a very common range you'll see is going to be kind of this whole area here, and that's going to be just your alkane, right? Alkane, alkyl type, just CH groups. So this is a good little chart showing you where you could generally expect to find your different peaks depending on what the functional group is. So this is very helpful if you're given a problem where you have protons labeled like A, B, C, and D on a compound, and you have to say, okay, which peak corresponds to which of these? Well, if you have hydrogen A, that's an aldehyde hydrogen, you say, okay, it corresponds to the peak around 9 to 10. Right, so you can use the chemical shift to help you determine specifically what signal is corresponding to what hydrogen. So in the last video on NMR, I'm going to go over a few NMR spectrums and figure out the structure of our compound from those spectrums.